Hey, good people, we are in chapter 9 and we're finishing up this chapter and we're going to look at two more types of nonlinear functions, which are cubic functions and exponential functions. So let's get started with a little bit of vocabulary. So when we talk about a cubic function, it is a function that has its form as y equals ax cubed plus bx squared plus cx plus d. And hopefully this is somewhat reminiscent of the quadratic function, which we remember to be y equals ax squared plus bx plus c, or even the linear equation y equals mx plus b, right? If you notice, there's a definite similarity here. What I want you to notice is if a is equal to 0, that whole term goes away and we're left with basically what would be a quadratic equation. Similarly, if a was equal to 0 here, we'd be left with a linear equation. So there is definitely a relationship among them. But now when we talk about what a cubic function is, right? We want to think about what it looks like. And so a cubic function could have a wonderfully delicate curve that looks like that. That happens. Or it could have a very exaggerated curve like this. There's a quality with all cubic functions that they have, in a sense, 1, 2, 3 possible turns. That's the most number of turns. Or they're going to start off high and end up low, right? Starting off high and then they end up low, or start off low and end up high. In any case, you're going to see something like that happen. So that's typically what a cubic function is going to look like when you graph it. Now, an exponential function is a little different. It's a lot different, in fact. When you have an exponential function, you're going to have y is equal to some term a, right, times b raised to an x power. A couple bits of information you need to know. So notice that the exponent is a variable, which is not something that we've seen before. Here we had numbers as exponents, but here the exponent is a variable. So that's going to be really interesting. The next thing we need to know is that you've got a times b to the x power. B has some restrictions on it. B cannot be 0. Nor can b be 1. If b is 0, it would be 0 to an exponential value, and that's still 0, times a, that's still 0. This would simply be a linear equation where y is equal to 0. We'd have a horizontal line, or the line that lays right over the x-axis. So that's not going to be acceptable, nor is it okay for b to equal 1. And let's think about that real quick. If b were 1, we'd have 1 to the 0 power, or 1 to any power for that matter, is 1. So then we'd be multiplying 1 times a, which really is just a. So again, we'd have a horizontal line at y equals a. So other than those two restrictions, b can be any number. And b can't be negative. So that's another thing. So b is greater than 0 such that b does not equal 0 and b does not equal 1. And so those are our restrictions on exponential functions. One more little thing, sorry. Y is equal to a times b to the x power. You could also have another c term where you're adding a term or even subtracting a term from the actual function. All right, now that we've got that together, let's look at a couple of examples. Example 1 has 2 parts, so we're going to make sure and leave space for part A and for part B. So in this case, we're going to graph the cubic function. And the beautiful thing about graphing any function is that they all work if you simply make a t-table. However, or XY table. However, when we make an XY table, we need to be mindful of the type of graph that we're attempting to graph. So when I'm graphing something like a cubic function, I may choose numbers for my x value that are surrounding the origin, surrounding 0, or on either side of 0 that is, but are kind of close. So notice we've got -1 and -1.2, which we usually see us use integer values, but we're going to use these values and see if we see any kind of pattern. So here I have -1.2. When I plug that into the equation, I calculate and I get approximately -3.5, which gives us this point. Putting in -1, do my calculation, I get a -2. Notice -1 to the 3rd power is -1. And then I'm going to multiply that by 2. I get a -2, which gives us this point. When I plug 0 in, clearly 0 to any power is 0, and then I'm multiplying that by 0, and I get this ordered pair. It goes through the origin. And then look at the following pairs of calculations and the numbers that we got. Notice that -1, -2 is kind of like 1, 2, and -1.2 and -3.5 is kind of like it's kind of like 1.2 and 3.5. What you'll notice is that there is a type of symmetry here. It's not like the parabolic symmetry that we saw when we were dealing with the parabola, when we were graphing the quadratic equation, but the symmetry that we're going to see here is actually a symmetry about the origin. It's kind of like the same here and the same here. It's almost like it's rotated around, right? If you could imagine taking this leg and rotating it around right here at this point. So that's the kind of symmetry that's being displayed here, and we see that delicate and beautiful curve that we're used to when we think about a cubic function. Let's go ahead and look at the second portion of example 1. So here's example 1 continued. So again, we're going to choose some values for the x column, and again we're using some decimal values, which is not that big of a deal. Unfortunately, I just revealed our graph, but that's okay. Let's see how we got to the graph. We get to the graph by plugging in these values, and we're going to plug it right into the equation. And so when we plug in -1.5, we end up with -0.4, so that gives us this point. Plugging in the next value, we end up with this point. Plugging in 0 is usually easy. When we plug in 0, we end up with +3. And we're going to look at our graph and compare it to other graphs in a moment. And so here is our value when we plug in all of the values that we have here listed for x. And here's the result in ordered pairs. So when I graph these ordered pairs, as you can see here, I get a really nice, beautiful curve. Again, it's really helpful to know what you're looking for. When you know you have a cubic equation or a cubic function, you know that the graph is going to have this curve or a curve that's similar to it. So you're looking for the curve when you're choosing points to represent or to be plugged into the equation to actually figure out what the graph looks like. All right, let's move on to this next example. Example 2 is going to have us investigate cubic functions in a different situation. So cubic functions are often very valuable in describing certain phenomena in life, and the one that we're going to talk about here is the volume of a cone. In this case, the volume of a cone where the base has a radius of x and the height is also x is represented by this function. So y is equal to 1/3 times 3.14 times x to the third power. I'm hoping you recognize that 3.14 probably more precisely should be pi. However, we'll use 3.14 because that's a decent approximation. So again, here we're graphing the information in the first quadrant. We know that means positive x values, so it makes sense that graphing 0, 1, 2, and 3 would give us these positive values, would be enough to give us the values in the first quadrant. So now that we've got that out of the way, we're going to plug in our values right in for x. When I plug in 0 for x here, I get 0. All of this cancels out, and this tells me that part of the graph is going to go through the origin. When I plug in 1 cubed is itself, and then I multiply 1/3 times 3.14, I'm getting approximately 1. It's pretty close to 1. And then, so that gives me 1, 1 as a point. When I plug in 2, I get 2 to the third power, which is 8. Multiplying 8 times 3.144 divided by 1/3 is going to give me something close to 8, actually 8.4. And finally, when I take a 3 and I plug it in there, I'm going to get 27. Multiply that 27 by 3.14 divided by 3, I get 28.3. So I get these ordered pairs. When I do that, I plug them in or I plot those points the way I'm used to, and I get this graph. What I want you to notice about this graph is that this graph does seem to have like an arm of a parabola. But if we were to graph some negative values, and obviously negative values don't make sense here if we're talking about the lengths of an object, but the negative values would give me a graph that does something like that. So I would see that curve that we're used to with the cubic function if I were to plot more points. So that kind of reminds me that I need to be really discerning when I look at a graph and try to determine what it is. All right, let's move on. So our example 3 gives us an introduction to exponential functions. So we're going to look at some exponential functions here. So Hannah sends a text message to 2 of her friends. Each of her friends then forwards the text message to 2 more friends each. Each of those 4 friends now send the message to 2 more people. So you can see this is information that's spreading rather quickly. What we need to do here is recognize that this relationship, n is equal to 2 to the x power, represents the total number of text messages sent at x stages of the text message. So what I'd like to do is think of Hannah, pardon me, having her text message to herself as the beginning, as to the 0 power. And 2 to the 0 power is 1. One person had the text message. And 2 to the first power, after she did the first thing, which was to send, or after the first stage, she sent it to 2 of her friends. There were 2 people with it. After the second stage, where her friends sent to other people, there were 4 people who were now given the text message. So let's go ahead and look over here at how we can organize this information. So we start off with our stages being 1, 2, 3, and 4, and then we're going to calculate the number of people receiving the text message at each stage. So we can see when I plug in 1, I get 2 to the first power is equal to 2. And then I see that my ordered pair is 1 for the first stage, 2 for the number of people who receive the text message. Continuing on in that fashion, look at the ordered pairs that I have. So these ordered pairs are going to inform where I'm going to plot points in order to figure out the graph of the exponential function. And when I do that, there's my exponential function. Our exponential function goes up rapidly, quickly. More quickly than any other function, as a matter of fact. Well, any other function that we've studied thus far. So that movement up is very quick. It started off slow and it goes very quickly. If we were to actually graph backwards, we would see that if obviously negative numbers don't make sense here in this situation, when we think about negative text messages sent. However, if we were to graph backwards and use negative numbers in this equation, we'd see that we'd have a line or a curve that rapidly approaches the x-axis. The relationship that that x-axis and that graph have together is called asymptotic, and in that case, x-axis would be an asymptote for the function. We'll talk about that later. Let's go ahead and answer this question. In what stage will there be 64 text messages sent? And that stage, if you haven't guessed it already, would be at the 6th stage. All right, and you can think about that as 2 to the 6th power equals 64. We're going to do our final example for the lesson. So this example has, again, another exponential function, but we notice that we're adding something here, and that's going to change exactly where our exponential function lies. So let's see what we have. So we're going to choose some values again. I like choosing positive values and negative values if I can, and what's done here is that we've done exactly that. So we're going to plug in -2 right in for x, and calculate. Well, 2 to the -2 power is really 1 over 2 to the 2nd power. And if 1 over 2 to the 2nd power is what we're calculating, that's just 1/4. 1/4 plus 1 gives me 1 and 1/4, or 1.25. So we realize when we plug in a -2, we get 1.25. If we continue with that reasoning and that logic, plugging in x values and calculating the corresponding y value for those x values, we would end up with the set of points that we see here. Now we're going to graph those, and when we do so, we get this. Again, a rapidly increasing function on one end, but on the other end, a function that has an asymptotic relationship with the line. Now, if you notice, this 1 did not actually give us our y-intercept, but what it did do is it took the function and lifted it up 1. All right, listen, that's all I have for today for you guys, right? So we can talk a little bit more about this. Realize we're touching on a heavy topic with very gentle hands. So if you have some questions, please feel free to ask them. I'm looking forward to talking to you about this and anything else in math. I'll talk to you guys later. Bye-bye.